recording? Okay, now we're recording. That's good. Let's go here for the notes, and we also have to take a look at the syllabus. First thing I want to do is change here the schedule. We're gonna, okay, first thing that I'm gonna do, I'm going to change the first exam. Okay. Switching here. The partial exams are going to be on a little bit later, okay? And let's see, let's first update it here. O2, save it. Need someone. Juneteenth. Oh, by the way, there will be a holiday, huh? There'll be a holiday next Monday. Weekday is Monday, Juneteenth, and this lab we will have to do some other time. I will adjust that later on. Let's see. Let's see if I can do that right now. Lab 3. Yeah, let's do it right now. Lab 2. And lab 1. Here's going to be lecture as well. I will figure out what I'm going to do is the CL here. Leave that for now. Maybe we do it on Wednesday and on Thursday. Otherwise, we do it together with this first lab. Okay. Today is the 13th. That's the Thursday. Okay, save it. Yeah. Good. So that's what we have for the changes in the syllabus for now. Final exam. I'm planning the final exam at 8 a.m. Okay. 8 a.m. For the other partial exams, I want first to lecture, and then we take 2 hours, 8 a.m. to 10 a.m.
I have a question.
Yeah.
So on your calendar it states lab 7. I purchased the lab manual from Amazon.
Yeah.
From the direct link that you have, but it's blank. Lab 7 is not there.
Oh yeah, that's right. I got that's something that I have to fill in there, but I will brief you on that when it gets to lab 7. Okay.
Okay.
And I'll try to fix that before the end of the semester. Final exam, late a.m. to 10 a.m. Let's put it this way. And I will say, oops. And what we want to do now, we want to pick up where we left yesterday. Okay, so the first thing that we did here was yesterday was simple harmonic motion, mass attached to an ideal string that's called simple harmonic motion, SHM. 1, 2, 3. What comes next is not exactly the same, but it's very similar. Simple pendulum and the physical pendulum, they are quite similar to this simple harmonic motion. They're not quite simple harmonic motion, but up to a first order approximation, yes, they are considered simple harmonic motion. Okay, and that's what we're going to do today. It's the simple pendulum. So let's see how the simple pendulum looks like. The simple pendulum looks just like something like that. Right? If you were to do step by step, we would, well, we're gonna leave this way. Okay, it's going to be just a string and a bob, a mass that is small enough compared to the length of the string. Okay, and the length of a string is considered to be from the point of support, from the point of attachment, all the way down to the center of mass of the bob. When I mean the mass is small enough, what do I mean? The mass is the size of the mass is negligible compared to the length. What do I mean? I mean that the diameter of the mass is less than 1/10 of the length of the string. That's a very good rule of thumb to have every time that we say that something is negligible. If something is negligible, it's going to be 10 times less than another dimension in the problem. Okay, and this bob is small compared to the length of the string. What does it mean? It means that the diameter of the bob, or the largest length of the bob, is 10 times less than the length of the string. In order to solve this problem, we have to come up with our free body diagram that we learned in physics 37. Okay, the free body diagram here indicates that we have a weight. One of the forces is the weight, the other force is the tension. The tension in the bob, the tension applied by the string. And with those two forces, we can start to solve our problem. Remember, right? The free body diagram is nothing but an illustration of one of the equations that you're going to write down. Going back to our notes. Okay. Three forces. There are not three forces, two forces, right? There are only two forces applied to the bob of simple pendulum. The weight of the bob. That can be a third. It's possible that we have a third force. Yeah, the air resistance. But the air resistance is negligible compared to the low speed of the bob. That's why I put 3 here. But in practice, there are only two forces. So in practice, there are only two forces for this specific case of the bob. There will be some problems in which the air resistance, not just the air resistance, but let's put that the fluid resistance is not going to be negligible. There will be cases in which the fluid resistance is not going to be negligible, but then we have to account for that force. Okay, we're not going to do that. So now we start with the apply Newton's second law of motion. We gotta go and start writing our equation. I'm going to use this one here to help me out. Start writing the equations, and net force is going to be what? Net force is, I'm gonna have to do it a different way. Here we go. Net force is going to be the tension in the string plus the weight of the bob. Okay, and this relation must be equal to mass times acceleration, ma. And by the way, did I use a capital M there? Yep, I use a capital M, and so let's use a capital M here as well. Okay, now not strictly speaking, right? So now we have to look at our coordinate system. We have this one here. Okay, we have to look at our coordinate system. If we choose to use the Cartesian coordinate system, okay, well, let's put it here. And let's say I put my Cartesian coordinate system axis right here at the spot, at the point of lowest, the lowest point of the then what we're going to have, we are going to have two equations that's going to be a function of that time, x and y position, okay? That would be our first thought about solving this problem, but we can do better than that. We can do better than that. So right from the bat, you can see that the x position of the bob is going to change as time goes by, right? As well as the y position of the bob. The y position of the bob is going to oscillate between these points here. The x position of the bob is going to oscillate between those two positions. Okay. So if you choose a coordinate system just like this one, you're going to get a solution that's going to be both axes, x and y are going to be a function of time. Okay. However, we can do better than that. We can do better than that. Instead of choosing a coordinate system at that spot, we can choose a coordinate system with an origin somewhere else. Okay. Here you go. If you choose a coordinate system with an origin right here, and then I'm going to put origin O prime or 0 prime, notice what's going to happen. The bob, the distance from the origin is going to be constant all the time, because the string is always going to be stretched. Okay, and the only thing that's going to change is going to be this angle. Can you picture that? Okay, that's very important to choose a proper coordinate system to make it easier for you to solve a given problem. And what we have right here is not the Cartesian coordinate system, the distance from the origin and the angle with respect to the horizontal. In this coordinate system, we have just one parameter that is a function of the time. The distance from the origin is going to be constant. Okay, it's just the angle with respect to the vertical that's going to change as time goes by. This is the polar coordinate system. This is the polar coordinate system, and that's the one we are going to use. Okay, let's write that down. Sometimes those things are not obvious, especially when you look at and here, what you have right here is independent of your coordinate system, okay? This equation that I wrote down here is independent of your coordinate system. It's a very generic equation that doesn't depend that is written exactly in this way, whether it's in the Cartesian coordinate system or it's in the polar coordinate system, right? If we choose the Cartesian coordinate system, okay, we will get a solution for x and y, which are a function of time, or right, x as a function of t and y as a function of t. However, we can do better. However, we can do better than that. Note, see that the distance of the center of mass of the bob to the point where the string is attached is constant. Okay, constant and equal to r and equal to L. The only thing that varies, is the angle that the string makes with the vertical. I call this angle the angle theta, which is a function of theta. Okay. In this coordinate system, we have a single variable that changes in time. And this coordinate system is called the polar coordinate system that you must have seen before, right? Coordinate system. So one more student coming in. Here you go. So now we can write down our equation in terms of this coordinate system, okay? In the polar coordinate system, we have the polar coordinate system that has r and theta, right? The coordinates r and theta. Where r is a constant equal to L. So now we can go ahead and rewrite our second Newton law in terms of these coordinates. Okay, so I'm gonna remove the F net here, and I'm just going to write down the R component of the tension, the R component of the weight, which is going to be mg cosine of theta. Okay, but there's one more thing, and here I'm going to write down the acceleration along the r direction. Okay. Okay, so now, but let's take a look at the drawing again. Okay, so let's see if we did everything right here. So here you go. We are going to have, this is the, let's see if I have another illustration here of the r and theta. Yeah, it doesn't look like I have it. Okay, so here's my theta angle. Okay, and we are going to have a unit theta angle along this direction. That's simple. Okay. Oh, and by the way, that it's supposed to be theta hat. Okay, I cannot put theta hat in there. Theta hat. I'm gonna write it down. Hat. And he always does something like that. Oh gosh. Yeah, he always assumed that the first letter is going to be a capital letter. And just put theta hat. And here you're going to have the r hat, right? The r hat vector. I can put anywhere I want. R hat. I'll get a better notation very soon. R hat. Okay. So that's my first equation in the hat direction, r hat direction. And what else? Okay, I take a look at the tension here. The tension here is pointing in the negative r hat direction. Okay, consequently, we must have a negative sign right in here for this tension. And don't forget this guy here, I'm assuming that's a positive number, right? So let's put that, assuming that TR is greater than 0. That's why I put the negative in there. What about the mg? That's the mg. I'll put the mg here on the other side. Okay, this mg, here we have an angle theta here. It's not a hat. If we extend this line and if I extended this line here, this angle must be the same as this angle. And the hat component of my weight is going to be mg cosine of theta. Mg cosine of theta, okay? Equal to a sub r. Then we have to do the same thing for the theta component. The theta component is going to be sine of theta. Okay, and then we should have let's see, theta. Okay, and now let's study carefully whether we have a theta component or not, right? For the tension, here's the tension. No matter where this ball is, where this mass is, the tension will always point along the r radial direction. So the tension doesn't have a theta component at all. Okay, and so going to the next step, this guy here is going to be 0, right? And then we have to worry about the component of the weight along the theta hat direction. Theta hat is supposed to be in this direction, and the weight, the theta component of the weight is on the opposite direction. So we must have a negative sign here. Okay, and here is not AR, here is going to be A sub theta and A sub theta, step by step. Okay, so I will here write those two components here in the next line. Those are my equations, and I'm even going to write something. Oh, there is one more thing here that I gotta tell you, because the distance from the origin is constant. There will be no radial velocity whatsoever, and there will be no radial acceleration either. So this term here is going to be 0. Okay. This term here is going to be 0. And we can here write this set of equations again. This is going to be 0 here. Like that. And I'm going to put m theta on the left side. I can also cancel the m on both sides. Okay. And I'm going to solve this equation also for the tension, right? The tension is going to be like that. Let's put this way in case we need it later on. Okay, so well, there is one more thing that we can do. Going back to our illustration here. This bob, this point mass is going to describe an arc in space. Okay? An arc S. Okay? Don't forget that what we have right in here, you know, when I rewrite that again, is going to be something like that. It's going to be the second derivative of theta with respect to time. Well, it's not exactly the second derivative of theta, but I'm going to say even better. It's going to be the second derivative of the path length S with respect to time. So here you go. There will be an arc described by this bob, and the length of the arc is going to be equal to S. Okay? So where S is the arc length described by the bob. This arc length is related to the angle theta by, there's a relationship here between them, S equal to L theta. That's the very definition of angle. That's the very definition of angle. Okay. And then we can go forward to another step here. We can take another step. It's a little bit, the simple pendulum problem is a little bit more difficult to solve mathematically compared to the mass attached to the spring, okay? So now I'm going to replace L theta here in S. L is a constant. We have this relationship, and then we finally got our differential equation. Okay. Remember, we still have that other equation for t that we haven't used yet. Where is that? This one here. I'm going to bold face it so you don't forget about it. I'm concentrating only on this equation here right now. Okay. So what you see right in here is the linear acceleration. That's what you see right here. And what you see right in here is the angular acceleration. And again, what you see here is the linear acceleration as well. The linear acceleration in the along the theta direction. Now compare the above. Compare the above differential equation with the previous one we derived yesterday, right? Derived yesterday. I'm going to put them side by side. Let's go back here. One more student coming. Good. This one here, compare that. Yeah. Okay, that's what we got yesterday. That's what we are getting today. And I'm gonna go even further than that. I'm gonna put the L on the other side. Okay, so look what we have. We have a second derivative here. We have a second derivative here. Okay, second derivative. We have a negative sign. We have a negative sign. We get a constant. We have a constant. We have our parameter for position, right? One is linear position, the other is angular position. But then there is a major difference. The difference comes here. This one is x, this one is a sine of x. Okay? So in principle, the solution for this equation is not the same solution as this equation, in principle. Okay? However, depending on the conditions of the angle theta, the solution of this equation is going to be exactly the same solution as this equation here. Okay? And it's going to depend on the conditions of angle theta. You know? These two equations, right, are almost the same, almost the same. The only difference is the sine of theta on the right side. On the right side. Ooh. Symbol. Okay. That's the only difference. However, these two equations can be made exactly the same if we adopt one important approximation. Okay. One important approximation. You know, the approximation for small angles theta. Okay. So you should remember that for small angles, okay, for small angles, we have the following. Sine of theta is approximately equal to theta. Do you have ever seen this approximation before? I can prove that to you just by testing the values of sine of theta and theta. Okay. And that's something you can do as well. You can do that in Excel. Okay, I have Excel here. I'm gonna close this window because we don't need that. And I have my roster here, and I'm going to prove to you that this approximation is a very good approximation, by the way. Have you ever seen that before? Anyone of you have seen that demonstration that for small angles theta is approximately equal to sine of theta? I want to hear from you folks. Anybody has seen that? Do you believe in this approximation?
Can you repeat that, Professor?
Yeah, the question is, this one here. Do you believe this approximation? Do you believe in this approximation?
Yeah.
Yeah, but the next question is, one thing is to believe, right? The next question is, have you ever seen the proof for this approximation?
The derivative of sine near 0 is 1, very close to 1, and at 0 is exactly 1. So small angles are approximately it's called a linear function of just x.
Okay, that's a good way to look at that. Yeah, but then you have also to tell me what means this approximation is going to be good within which values of theta, right? That's the next question, right? Then the next question is, this approximation is good within which values of theta, right? Yeah, that's a good way of explaining that. Okay, I'm gonna do that right now in Excel. Okay, let's do that. Here you go. I'm gonna have sine of theta here. I'm gonna have theta there and sine of theta. I'm gonna just spell out sine of theta so I don't have to get into trouble here. Okay, and by the way, it's gonna be theta in radians and yeah. Let's put theta angle degrees and theta degrees. Okay. So let's start with 0 degrees, 1 degree, 2 degree, and so on, right? And here you go. I don't need to go the full circle. And we're just doing a little pause here before I continue. Let's see, view. I want this one here, freeze panes. Good. Okay, so here you go. Radians of this degree. So 0 degree corresponds to 0 radian. 1 degree corresponds to 0.017, and then we are going to do the sine of theta. Unless you tell Excel otherwise, the theta must be in radians. Okay, and here you go. I'm taking the sine of theta for different angles right here. That's one possible way of proving that, of demonstrating that. There is another way that we can do with Taylor series, and then there's this other way that you mentioned, right? So let's compare here. At 1 degree, radians is 0.017 and sine of theta is 0.01745. The only difference is in the last decimal place here. Okay. So definitely, this is a difference of less than 1%. I even gonna, percentage difference. Even going to calculate the percentage difference. The percentage difference is 0. I'm not even going to do the math. Now here you go. This one, absolute 1 minus this one divided by 100 times 100 divided by the actual value. See, we're having 0.005% difference. Okay, and as we move forward, the difference becomes larger and larger. Okay, at 10 degrees, we have only 0.5% difference. Only 0.5% difference. Okay, above 10 degrees, let's say to 20 degrees, the difference grows up to 2%. And then let's say at 45 degrees now, this difference grows up to 11%. For the sake of this course, everything less than 10% is negligible. Okay, so for the sake of this course, we can say that that approximation that you see in there is good up to 42 degrees of angle. what we are taught is different, right? But nobody tells you. You know, what we were taught is that this approximation is good to whenever the angle is less than 10%. Well, you know, the better way of saying that is that whenever the angle is less than 10%, the percentage difference is less than 0.5%. Okay, and this percentage difference keep on increasing as the angle increases. Okay, so what I can tell you is that what we can say is that that approximation here, you know, this approximation is good within 10%, right? Up to 45 degrees. Okay, so let's go back now to our differential equation, and now we can finally here write our, and I'm going to put an approximation here to remind you that this is not an exact solution. Now those two equations are exactly the same. We have the differential of a parameter, the second differential of a parameter. The parameters are different, but overall the equation is the same because we have a negative sign here, a negative sign here, a constant here, and the constant multiplying your parameter. Okay. So based on this solution here, we can state that the simple pendulum behaves like a simple harmonic oscillator whenever the angle is small. Okay, so we can write that down, which was exactly the observation that Galileo made. I covered that, right? According to the above approximation, the simple pendulum behaves like a simple harmonic oscillator whenever the angles of oscillation, the angles of oscillation are small. And by small, you know, we can estimate, by small we mean less than 10% error for a maximum angle of 45 degrees. Okay, and less than 0.5% error for an oscillation for a maximum angle of 10 degrees. For a maximum angle of 10 degrees. Whether you're going to use this approximation here or the other is going to depend on how picky you are. Okay, you go. One, less than 10% of error for a maximum angle of 10 degrees, and less than 0.5% of error for a maximum angle of 10 degrees. Having said that, now we know what the solution for that is. Okay, just recall the solution of your x. Let's go back to our yesterday's solution. Here you go. That's was yesterday's solution. Yesterday's solution, right? Today's solution, and then we have to replace the x with theta naught, which is the amplitude, and you have to replace the k over m with the other parameters g over l. Okay, for the initial, and then that's for the following initial condition, right? For the following initial condition. initial condition, theta at t equal to 0 equal to theta naught. Okay. Theta prime at t equal to 0 equal to 0. Just like we had for the x last time. 8:54 right now. Okay. Just like before, we have a period. Oh, what about the period, right? Let's take a look at the period that we got before. I'm going to get the equation for the period of my SHO, simple harmonic oscillator. Here you go. That's the period of our simple harmonic oscillator. I'm going to even specify SHO, right? And then we have the simple pendulum, G over L, G over L. No, it's not G over L, wait a minute. K over M is L over G. Right? L over G. You can even do dimensional analysis. Here we have meters. Here we have meters per second square. Second square goes upstairs. Meter cancel out. The square root of second square is a second. SP for simple pendulum, SHO for simple harmonic motion, simple harmonic oscillator, or simple harmonic motion. Okay, so that's what we can do for the simple pendulum. It's 8:56. Let's take a little break now. Before you take a little break, any questions about that? Okay. So let's take attendance here, and I'm going to relabel attendance. Eugene Choi, are you there, Eugene? I don't see Eugene here. Don't forget, I give like 5% grade for attendance. Ashley too. Ashley, I don't see Ashley here. Let's see, Zakir. There he is. I don't see Zakir either. Amy. Okay, not here. Andy. Andy is here, right? So you're here, Andy.
Yes, Professor.
Okay, thank you, Andy.
Yeah.
So Alex Hernandez. Looks like Alex is here. Hi, Alex. Just say that you're there. You're not away from your computer. What I usually do if you don't answer, right? Within a reasonable time, I put a star here just to remind me that you were listed in my participant, but you didn't answer to my call, my roll call. Emily who? Emily, I don't see Emily either. Shartak. I don't see Shartak either. So Stephanie was one of the first ones coming, right, Stephanie?
Yes, here.
Okay, thank you. Zaid? Hi, Zaid, are you there? Oh, right, thank you. You raised your hand there. Alisa? I don't see Alisa there. And Kartika?
I'm here.
Thank you. Mary? Mary seems to be here. Okay, Mary sent me a message earlier on. I'm gonna give her Attendance, Raymond. Raymond is not here today. Ashley Tai. I don't see Ashley either. Oops. Kyriakos. I don't see Kyriakos. Alexis Valley. Are you there, Alexis?
Yeah, I'm here.
Okay, thank you. Joshua is here, right?
Yes.
Okay, thank you. And Basilio also is here. Daniela is not here. So we have a total of 8 students who replied to my roll call. Let me see, Alex Hernandez. Are you there, Alexis? I put a star here in your attendance. Okay, the star is going to stay there, and let's take our break. First break, 9 a.m. to 9:15 a.m. Okay. So I see you in the next 15 minutes. Okay. So, okay, I'm back here. And that's what is, don't forget, simple harmonic. We did mass attached to a spring yesterday. That's called simple harmonic motion, like motion of a mass attached to a spring. SMH and simple pendulum. Simple pendulum. Okay, can be reduced, can be approximated, right? Approximated to simple harmonic motion, right? Simple harmonic motion. Can be approximated to simple harmonic motion whenever the amplitude of the pendulum is very small. Pendulum is very small. Some people say, most people say less than 10 degrees. Okay, but as you saw, but you still can get a percentage difference of less than 10% whenever the amplitude is less than 45 degrees. Okay, most people say less than 10 degrees, for a 0.5% difference, right? But you still can get a percentage difference of less than 10% whenever the amplitude is less than 45 degrees. Okay, so what we are going to do now is the physical pendulum. Physical pendulum, which, by the way, is very similar to the case of the simple pendulum. And let's take a look at our illustration here of the physical pendulum. Let's see if I can find it. Okay, here you go. Here's a physical pendulum. Here's an illustration of a physical pendulum, but it can be something far more generic than that. It can be something like that, a rigid body that has a center of mass. Okay, and this rigid body is attached to a point where it can freely oscillate with no friction. Okay, that's the local vertical. That's the distance of the center of mass to the point of oscillation. Okay, D. And those are the things that you have to know, okay? Because it's a rigid body. This rigid body has a moment of inertia I, mass M, and moment of inertia I, okay? So let's write down that in our writing here. This one here, physical pendulum. Rigid body of mass M and moment of inertia I. And distance of the center of mass to the point of rotation D, right? Okay, this is the center of mass to the point of rotation D. And we already identified all the forces in there. You know, solution, right? Find the equation of motion. Equations of motion, right? You can write that down, equations of motion of this physical pendulum. We can treat that as a problem. And then we go for the solution. Okay? Forces. The weight. Forces, the weight, mg. Okay? Forces applied to the rigid body. Because it's a rigid body, now the equations are slightly different, okay? Okay, because we're dealing with a rigid body, the equations we're going to use are slightly different. In the previous cases, okay? Previous case, we were dealing with point masses. For this reason, we could use Newton's second law. Second law. But in this case, we're dealing with a rigid body. For this reason, we must use Newton's second law for a rigid body, not for a point, right? Not for a point particle, not for a point particle. And then we saw that in physics 37. The Newton's equation for a rigid body is not net force, okay? It's something else. Newton's equations for a rigid body, not Newton's equation, but let's say, you know, the Newton's equations for a rigid body is not F equal to ma, but it's something else. It is, oh, let's see here. It's the torque, it's the net torque, right? Net torque equal to I times alpha. We saw that in physics 37, right? So we go. Let me just put that by side to Newton's law. Here you go, MA. I didn't put the vector sign there. That's what we use for a rigid body. IA. We know the inertia. I'm going to emphasize here that we do know the inertia. We do know the mass. We do know the distance of the center of mass to the point of rotation. Okay. And the net torque. You know, we're going to have, by the way, we don't have just one force. We have one more force there that I didn't mention, because this force doesn't come into play, okay? But I am going to mention anyway. In addition to the weight of the rigid body, we also have a normal force here applied to this point of rotation. I didn't illustrate this normal force, okay? This normal force is at a given direction. We do not know what the direction of this normal force. Okay, but it's somewhere in upwards. Yeah, it should be upwards, because otherwise the body will be falling, right? At least it must have an upward component. But we don't need to know this normal force. We do not need to know this normal force because it doesn't have any torque applied to this point. The normal force is being applied at a point of rotation, and the torque of the normal force is going to be 0. Okay, but I want you to be aware of this force anyway. So the net force is going to, the net torque is going to be given by this, the torque of this normal force, plus the torque of the weight. Torque of the weight. It's going to be like that. Don't forget the torque is also a vector, right? Quantity. But because the normal force, okay, because the normal force is being applied, because the normal force is applied to the point of rotation, then its torque is 0. Okay, so let's write it down. We're going to write this equation right in here. There's going to be 0. We are left with the torque of the weight only. Okay. And we have to find out what is the torque of the weight. And then, in order to find out the torque of the weight, we have to go back to our illustration. At this point in time, at this specific point in time, right, the torque is working against the angle theta. Here's the angle theta. This angle theta is the same as this one. This angle here is the same as this angle here. So the weight is applying a torque that's going to be given by mg sine of theta. Okay, but because the torque is in the clockwise direction, the angle is being measured in the counterclockwise direction, it means that this torque is going to be negative with respect to the angle theta. Okay, so just like we got for the pendulum, right? Just like we got for the pendulum. Is right here, sine of theta. So let's write that down. Is going to be minus mg sine of theta. Mg sine of theta. And we are left with this equation here. Which, by the way, can be reduced. Alpha is the angular acceleration, remember that? Angular acceleration, and I, is called moment of inertia, but I like to call it the angular mass. ego alpha is the angular acceleration that can be written in terms of the angular velocity, which, by the way, can be here written in terms of the angle theta, like that. Let's take let's put it in another format here. Now I'm gonna pass the I to the other side. Okay, and that's the relation that we end up getting for the physical pendulum. Let's put it side by side with the other one for the simple pendulum, right? Here you go. Side by side. Physical pendulum, simple pendulum. So what we have, d2 theta dt2, d2 theta dt2, a negative sign, a constant. Mass doesn't change, acceleration of gravity doesn't change, and it's because the rigid body, the moment of inertia doesn't change either. And we have sine of theta, exactly the same. Exactly the same. Okay? Exactly the same equation with constants that are different. Okay? So we reduced, right, the physical pendulum to an equation, to a differential equation that is exactly the same. That is exactly the same as the one for the simple pendulum. Consequently, the solution is the same as well. Provided, of course, provided you replace the constants appropriately, right? Well, so just like before, we must make an approximation for the sine for the sine of theta, right? Just like we did that for the simple pendulum. And okay, I will do that this step. We end up with an approximation here, theta. And the solution, which is going also to be an approximate solution. Ideally, we should put an approximation here, right? That I was supposed to do in the other one as well. Let's do that. So you know it is an approximation, but it's not any type of an approximation. It's a good approximation, a very good one. Okay. And instead of square root of G over L is going to be mg over I. Okay. It looks like I missed something here, right? I forgot one important piece here. What did I forget here? I got only the weight, right? The component of the weight, but we gotta put something else there that I forgot. Nobody picked up on that, huh? Don't forget, we have to put the torque here, which is the force times the distance, right? So here goes, must be a distance here, and a distance here, d, mgd over I, mgd, right? mgd. Okay, and this moment of inertia, by the way, is the moment of inertia with respect to the point of rotation. Because it's respect with the point of rotation, I am going to specifically state here that respect to the point O, right? The point O of rotation that should be the origin of our coordinate system. So you have to know this moment of inertia. I'm specifying that the moment of it is not the moment of inertia with respect to the center of mass. Okay. Okay. That is one of our equations of motion. Go. This one is one of our, then you can get the other equation of motion by differentiate that once and twice, right? And what else? We can go ahead and find out the period as well, just like we found before. Okay. Period. Period of simple pendulum. Period of the physical pendulum. That's going to be equal to I naught MGD. And I'm going to compare them all. Simple harmonic motion. And by the way, they are all approximations. I didn't put that either, but again, I'm going to emphasize those two are approximations. These one are exact solutions. Okay. And I have a table here that I'm going to paste into this note, comparing the simple harmonic oscillator with the simple pendulum and the physical pendulum. Okay. For the small displacement, there is no change here for the small, but there is a change here for those two. Okay. Angular to linear, yeah, we can change from angular to linear as well, right? Theta is S divided by L. And the solution, here are solutions. That's 937. Any questions? Oh, the period as well, right? Go. Everything comparing side by side. You compare side by side. Then we can go to the next one. Damped oscillations. That's the next in line here. Oscillation. How is damped oscillation? I'm going to give you an example of a damped oscillation. Damped oscillations are oscillations in the presence of friction. In the presence of friction. One example, I have here one example. Here you go. That's one example here of a damped oscillation. I want to give us even simpler. Yeah, let's stick to this one. Okay. One example of damped oscillation is this mass here submerged in a fluid. Okay. this mass submerged in a fluid. If it's in the vertical direction, there will be a buoyance there as well, buoyance term as well. And when the mass is moving, there will be a damping force that's going to be against. Oh, here you go. Okay, here you go. That's the damping force right in here. If the mass is moving upwards, okay, there will be a damping force that's going to go against the velocity. Here I'm showing all the forces here. Here's the force of the spring. Here's the buoyance force. Here's the weight, which by the way, the buoyance force is always constant. The weight is always constant. But this force here is not going to be constant. This force here is going to depend on the velocity. Okay, so here you go. Here's how we denote the drag force. We saw the drag force for the case of the skydiver. Okay, the skydiver is subjected to a drag force like that, that goes against the velocity vector. Okay, so depends what's the velocity vector of the mass, right? The damping force is going to be one way or the other. Okay, so we have to take into account this type of force. So let's so just a question of setting up our equations of motion. Okay, and I'm gonna get my, in this case, it's still considered a point particle. Okay, so we're going to have a net force equal to the mass times acceleration, just like we have according to Newton's law, right? Now it's a matter of identifying what those forces are. Okay, one of the forces is the spring. The force that the spring is applying to the mass. The other force, is going to be the drag force. And we have seen that this drag force can be approximated to that of is a constant times the velocity. That's one good model. Okay, the minus BV, right? Minus BV is the drag force for small velocities. So we have this fluid that's applying this drag force. Strictly speaking, the drag force is not BV. Okay, BV is just an approximation. Is an approximation, is the drag force, is the approximation, here you go, is the an approximation for the drag force, an approximation of the drag force for small velocities. But strictly speaking, okay, a more realistic model of the drag force, more realistic model of the drag force for any velocity is this one here. Is not this one here, but it's something like that, a different constant times the velocity square, okay? That's a more realistic model, but it's more difficult to solve for that for this condition here, for this reason that we are, however, theoretically, it is much difficult to solve, to obtain, right, the equations of motion, to obtain the equations of motion for this type of drag force. For this reason, that we stick to the approximation for the small velocities. So we're back to this one. That's our equation, which, by the way, is not much different from the previous one, okay? Here you go. I can is a one-dimensional type of motion, okay? We're talking about dt2, right? mdt2. And here we get the x dt, dx dt. That's the equation that we have to solve. I'm going to reorder it in terms of the highest to the lowest derivative term. Okay. And look what we are getting here. It's not much, you know, if you think a little bit, you're going to realize that this equation here, even though it's different from the other ones, it's not much different from them. Okay, we're going to go back here. We're recording.
Yes, you're recording.
Okay. Yeah, I'm recording. Let's go get it. This one here. It's not much different than what you see here. Here you go. I'm going to go the next step, right? Put the mass here and the mass here. We have the second derivative term here. We have the second derivative term here. We have k over mx. We have minus k over mx. The only difference is this term here. That's the only difference. But if you analyze this equation carefully, you're going to see that it's not, the solution should be not much different from this solution here. What this equation is telling you? This equation is telling you that whenever you differentiate your function twice, you get back your function times a constant. Okay, that's what you're saying here. That's what this equation is telling you. Now, what this equation is telling you is something similar. It's telling you that if you differentiate your equation twice, you get, if you differentiate your solution twice, you get the solution times a constant. But it says something else too. If you differentiate the solution twice, you get back the same solution, but as derivative of it, as its derivative. Okay, that's what this equation is saying. So if this equation has a solution in terms of the exponential, this equation will also have a solution in terms of the exponential. Okay. Makes sense? Okay.
Yes.
Both the simpler solution and the damped one must, but this both the simpler, let's see, both simple harmonic oscillator differential equation and the damped one must have solutions in terms of an exponential. Okay, we just have to figure out what type of exponential. We just have to figure out what type of exponential it is. Okay. One solution that we can try, is going to be something like that. Here you go, an amplitude, an exponential solution, and an RT. R is a value that we still have to find out, and can be either positive or negative. Both of them should be mathematical solutions. Okay, let's analyze each one separately, right? Here you go. Suppose it's a negative solution. If it's a negative solution, the solution here is telling us that the amplitude is decreasing as time goes by, right? That's what this solution is telling, assuming, of course, that R is real. Assuming that R has a real component, a real positive component, okay? Assuming that R has a positive real component, this solution indicates that the amplitude of the oscillator will decrease as time goes by, which is exactly what we should expect if we have a situation like that, right? We have frictional forces acting in the device, and with the frictional force, the amplitude should decrease little by little because mechanical energy is no longer going to be conserved. So we should expect the oscillation to decrease little by little. Okay. So the other mathematical solution, and I'm going to point out here, a reasonable solution, a reasonable physical solution. Okay. The other, that's the difference between mathematical solutions and physical solutions, right? The other mathematical solution, I'm going to emphasize that there is a positive sign here. It states that as time goes by, the amplitude is going to increase, not decrease. Okay, so here you go. Just like before, assuming that R has a positive real component, okay, this other solution indicates that the amplitude of the oscillator will increase, not decrease, as time go by. Increase. Here I'm going to emphasize decrease as time goes by. If the amplitude increases, it means that the energy of the oscillator also increases. Okay, this does not look like a reasonable physical solution. This does not. It might be a mathematical solution. It might be a mathematical solution, but it's not a physical solution. So we are left with this solution here. That must be the actual solution. Consequently, the first solution must be the actual one. Okay, and we can start working on this solution. So right from the bat, I identified two possible mathematical solutions and I eliminated one of them. We are left with the other. 954. Okay, so what do we do next? Next, we do not know, by the way, we still do not know what is the value of R. Okay. Next, we try to find R by substituting the solution into the differential equation. Okay, so let's go. Here's my differential equation. And then we figure out whether, we will find out whether, the equation makes sense. That's my x. The next one should be my dx dt. My dx dt is going to be minus RA. And the next one, d2 x dt2. Okay. Minus R. Okay, and then what happens to the negative sign here? Goes away. Okay. Now we substitute right here. D2x dt2, dx dt. And then the x. Okay. One more step. I'm going to cancel this negative sign. Okay, I'm going to cancel those exponentials. I'm going to cancel the amplitude. And I'm going to pass all those terms on the right side to the left side. And look what we have. We have a quadratic equation in R. We have a quadratic equation in R. So the solutions to this quadratic equation will solve our problem. Okay? And the solution just, whatever you have to do, right, to get the roots of this equation, that's going to be 2 roots are equal to a minus the second term, plus and minus, square root, the second term squared, minus 4 AC. C is K divided by M. And then we have to put everything under 2, like that. Did I forget anything? I'm gonna make it even simpler than that. You know, here you go. He's gonna get it. Well, I can do it here. B over M, right? B square over M square. Okay. What else I'm going to do? I'm going to do that. I'm going to put a M upstairs, and then I end up with an M square downstairs. Why am I doing that? Because I have M square downstairs here as well. When I do that, I can take out my M square from inside the square root. Right? And B, go like that. That's the solution for R. Okay. Now the question is what it looks like, the solution, right? What the solution exactly look like. A little bit lengthy, right? That's how it is. We have 8 students so far. Good. Well, first, you know, the solution to this equation, the solution to the motion is going to depend on the relative values of those terms here in the square root. Okay. We will start with the simplest one, that is B squared minus 4km greater than 0. Okay. If under this condition, the solution, let's go get it here. Here you go. It's going to look like the following. One of them don't forget I have minus R here, right? One of them is going to be minus all that stuff. Okay, I'm going to emphasize that there's a minus here. Okay. Okay. And by the way, I'm going to okay, leave this way for now. And so what we end up getting, let's see, minus, yeah, let's leave this way. We cannot go, we don't need to go any further than that. This solution obviously decays exponentially. Why is that? Okay. This solution decays exponentially no matter these two. So after that, we have two solutions, right? And yeah, let me get it. Let's do it better, like this way. Okay. And the other term. Yeah, no, like that. Here you go. And don't forget, because we have this minus sign, we're going to change the order of this term right here. Yeah, here you go. This term decays exponentially. This term with the negative decays exponentially as well. I'm going to do even, let's see. Let's see. Let's do that one by one, right? It's better if you do one by one. Here you go. Here you go. I want to put it in a better way. Here you go. Let's do the solution for R. We're going to analyze each one separately. R plus, let's look at the solution. It's better if you do this way. Yeah, good. And then we look at the other one, so you can see it more clearly. Here is going to be a positive. Okay. And no matter what, the solution is going to decrease. Okay. No matter what, this solution decays exponentially. Decays exponentially because this term here is going to be positive, right? This term here is going to be positive, but with the negative, it's going to be decreased exponentially. Now, what about the next one? A and B, right? I'm going to get now the negative here. I want to start with change the setting numbering value B. We want to do B here. Better. Like that. Even going to emphasize, we can leave this way. Okay, so the next one is going to be with this term negative. Okay. No matter what, the solution decays exponentially, and it is a physical solution, and it is a physical solution. The other case is 2b squared minus 4km greater than 0. If b squared minus 4km is greater than 0, this square root is going to be a real number. Okay. Then this one is a little bit more trickier, right? Because we are going to have two terms. One with a negative exponential, one that decays exponentially, and the other that doesn't decay exponentially, that grows exponentially. Okay. Okay. But this solution also decays exponentially because this term here, oops, is greater than this term here. No matter what. No matter what, it will decay exponentially. Okay. So one way to show that is by putting a parenthesis here. Right? And recognize that this term is greater than 0. Why this term is greater than 0? Because this term here is less than that. Okay? Make sense? Okay? Let's prove that this term is really greater than 0. All we have to do here is to pass the square root to the right side. Okay? You square both sides of the equation. Okay? And recognize that this term here on the right side is No, this b square here on the right side is being subtracted by a positive number here. So those two solutions, they are physical solutions. They do work, okay? And now we're gonna go for the other case, it's 10, 10, right? Let's see here, when was our last break? Let's take a little break now before I go into the next one. Yeah, let's take a little break, right? And then in this meantime, you see how you're going to do the other solution here. How are you going to prove that? Whenever b squared minus 4km is less than 0, okay? So what I want to do, break from 10:10 a.m. to 10:25 a.m. Any questions before we go into a break? I know it's lots of information, right? But you have to practice those things until you really master it. Okay. So I will see you in 15 minutes. Okay, I'm back here. And now, okay, so everything reduces to steady. What happens to this value, okay? And the most important part is this square root here. This square root can be real or can be imaginary. If this condition is satisfied, this square root is real. If the other condition here is satisfied, then this square root is a pure imaginary. In this specific case, the first case that we did, because the roots are real, you get a straightforward decaying of the oscillations, okay? So in both cases, you get a straightforward decaying of the amplitude of the oscillator. Here is a little bit more different. Okay, let's bring value. You go. It's a little bit more different, right? Because now your square root ends up being imaginary. Okay, so whatever goes right in here, in the square root, it ends up being equal to I times the square root again, but now the square root is going to be 4km minus b squared. 4km minus b squared, like that. And it doesn't matter whether it's positive or negative, right? Because we have two solutions. We're still gonna have a oscillating term. Let's go get it. It's this one right in here. Okay, good. Now I can put plus and minus because this term is going to be an oscillating term. And I'm going to break down this oscillating term. What you end up here is going to be plus and minus I 4km minus b squared. 4km minus b squared. And we can write that down in terms of sines and cosines, right? There you go. Cosine of this term here without the I, plus and minus, plus and minus I of the sine of this other term. Other term. Square bracket. I like to put that in square bracket. Okay, because the position is always a real number, then we must take the real solution of this equation. It's going to be like that. Let's take a look at some of the solution, how it looks like in the graph, right? In a graphical way. Let's go back to this one here, and not this one. This one here. I want this guy here. We first must come up with some numbers for the, for the parameters that we are talking about. B, right? M, K. And then we have the T. B will have its own unit. Okay, and we want B squared minus 4km greater than 0. B squared minus 4km greater than 0. So let's see. I'm gonna even put B squared minus 4km, just to keep track whether we are using the right numbers or not. You can plot that in Excel or any other software of yours. Superscript 4km. So let's get some random values here. 4km. Let's see, if you're gonna be greater than 0, we will have to have 4. 0.25, 0.2, right? B squared minus 4 k m greater than 0, right? If it's 0.25, okay, it's exactly 0. Because I used 1 and 1 here. So let's use 0.2 for now. And then we're going to start, let's say 1, 2, it's going to be in seconds. Maybe we need to adjust those values of t. Right? And the x. I'm going to put amplitude of 1 meter. 1 meter is too much, right? Yeah, let's put an amplitude of 0.2, 20 centimeters. And exponential b times t over 2 times m close parenthesis, another exponential. Let's see if I have it right. Yeah, it's going to be b squared, but it's going to be the square root of that. I'm going to put the square root. Divided by 2 times m. Okay, and then we have a negative number. We're supposed to have a negative number here, right? I didn't put the negative number, and looks like we got it. Okay, time t equal to 0. It has this amplitude. Let's see, I have to do something else here that I didn't do. Gotta put a dollar sign here. I gotta put a dollar sign here. I have to put a, where did I get my, okay. Yeah, I got it here, the dollar sign here as well. Okay. B2, go have a dollar sign. E. A, B, okay. So let's see if I got it right. Oh, I didn't multiply by time t. See. By time E, okay. Exponential, yeah, let's go. This one it was multiplied by E, right? E2. Let's see if we got it. Yeah, it looks like we got it. And as time goes by, this amplitude decreases just like we had predicted. Okay, and now we can plot amplitude versus time, insert chart. Okay, that's how, you know, that how should be the behavior of your oscillator. It started, you know, it started at maximum amplitude, right? Here's the position of equilibrium, and little by little it approaches the position of equilibrium. It doesn't oscillate past this point. Okay? It doesn't oscillate past that point. And let's take a look at the other case. The other case is b squared less than for mk, less than 0. Okay, so we can do that by making b equal to, no, not equal to 2. Okay, no, we have to do that. Let's say the k, let's do k. Yeah, now we got it. B squared minus k for km is minus 3. See that? And let's see, I'm going to repeat that in another table, in another spreadsheet. Move and copy, sheet 3, create a copy. Okay. Now, no, damp without oscillation. Without oscillation. 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 And then the other one is a damped solution with oscillation. Oscillations. And now I have to replace, you know, damp solution with oscillations. You know, this number here is going to be negative, and I have to change my solution slightly. I have the first one Okay, the first one doesn't change. Just be T over 2m. And the second one is a cosine square root of, let's see, I'm gonna get an absolute value here because we cannot take the square root of a negative number, right? Two m times t. Okay, now let's see if we can get it. Yeah, we do have some oscillation here. Just a little of an oscillation, see here? It passed the point of equilibrium, but it's still very highly damped. It reaches, have a little bit of an oscillation. Let's see if we can do better than that. Maybe we can decrease the damping. Right? Okay, we decrease the damping. Look what happened. Now we have two oscillations. In the previous one, we had just one oscillation. We could see just one oscillation. By decreasing the damping factor, we get more and more oscillation. Okay. Here, decrease the damping factor. Now we have 1, 2, 3, 4 oscillations, and so on, right? As I decrease the damping factor, I get more and more oscillations. But notice that we have an envelope that decreases exponentially, going back to the other one. Let's see what we had before. Yeah, 0.2. We have, a damping envelope both above and below. We can even plot this damping envelope. Both above and below. And that's going to be my upper right? Upper damping envelope. Let me envelope. Let's put it like that. And I will add this damping envelope. Select data. That's how I do it. That's how I add. And I'm going to add right in here, upper envelope. The X values are F. The Y values are this one. Let's see if we can get it. Yeah, we got it. For some reason, we got this point here. Let's see why you got this point here. 1, 0. Must be, okay, I think I know what this point is. I think it's this one here. Oh, what did I do? Yeah, I did something here. I don't understand what happened. Let's see. I will plot it all over again. Okay, here you go. Oh, let's do the lower envelope, up and down, and then we can plot them all together. Insert. Okay, now I got it. And I want to go just to 40. I don't want to go to minus 40. $140. Okay, here you go. That's the oscillation that you see. That's the upper envelope, that's the lower envelope. So you can do those simulations in Excel once you have the equations. If you want to make it look better, you can increase the resolution, right? Instead of going 1 by 1, go half by half. And Excel will update that automatically for you. Okay, here you go. That's the damping. $10.45, right? So did you get an idea how it works? Let's copy it and paste there, right? And in the notes, I'm not gonna label the axis, but under most conditions, you have to label the axis. And the snipping tool. Let's get my snipping tool here. Okay, that's oscillation with damping. Damping with oscillations. Okay. And the other one is something like that. Good. Okay, so go. 25. We have been going on for almost half an hour. Let's go to the next one. Let's see if I have any of that here already for you. Yeah, I do have it. I don't need that anymore, right? Because we did that before. It's always good to do that several times. Yeah, exactly. And then with motion. Go. And now we're going to do, that's from the last year's class. Now we're going to look at the forced oscillations. Okay, and this one is rather challenging. It's not easy. It involves lots of calculations, okay? And involves so many calculations that many books don't do this step by step like they are supposed to do. Not here, it's going to be right here. Okay. force oscillations on harmonic force and damping. And damping. Here you go. This is not damping. This is just the regular simple harmonic oscillation. Here is just, simple harmonic oscillation. SHO. Okay. What is X or Y? I put Y here. This one, damped oscillations. Damped motion. Okay. 1, 2, 3 solutions. Okay. This one has an oscillation. Those other two don't have oscillations. 3 solutions. The only difference between those two is the sign here in the square root, the one we just finished doing. And now forced oscillations. Forced harmonic oscillations. One good way of visualizing this forced harmonic oscillation. Notice that I'm going to put that on the other side here. So you can see, so you can be familiar with this term here, right? First, we did that harmonic oscillation. Then we did that oscillations is damping. And now we are adding this term here. That is, what's the role of this term? The role of this term is to add energy to the system. That's the role of this term. How can we visualize something like that? Okay. So we visualize something like that in the following way. Here you go. Here's the damped oscillations, right? So in addition to all those forces that you see, the force of the spring, the damping force, right? We still have the weight here and the buoyant, but those are constant forces. You don't have to worry about that. What else can we add? We add another force, another external force. It's possible to do that. External force. Oh, not this one. External force that varies with time. That varies with time. But it varies with time in a sinusoidal fashion. Okay? So think about that, the way to visualize it. Let me quickly stop sharing and then remind me to share again, okay? So you have your oscillator moving up and down. Okay? This oscillator has no damping factor whatsoever. It's the very first case that we did. Simple harmonic motion. Then you have the damped oscillator. Keep on decreasing its amplitude until it goes to 0. And now the forced oscillator, harmonic forced oscillator, you do have the loss in energy, but then this loss in energy is compensated by an external force that may be synchronized or not with the other one, okay? And this force will not let the harmonic oscillator to stop moving. Okay, that's what will be. Just try to visualize that. The oscillator here, and then we apply a force to it, whether it's synchronized or not. Okay, that's the type of equation that we are going to. That's the type of physical situation that we're going to look right now. Another way to look at that, is to visualize this, my pendulum, right? Let me try to get a pendulum here for you. Here you go. Here's my pendulum, right? The pendulum is oscillating back and forth. If I have a forced oscillation here, in this case, what do I have? I have this finger of mine that ensuring that any energy lost by the oscillator is added by the external force. And if my frequency of the frequency of the force matches the frequency of the oscillator, this oscillator may increase further and further, okay, until it completely breaks down. That's one way to look at that. And by the way, there are physical devices out there that use just that. Just like regular clocks, for instance, regular clocks, they must take their energy from somewhere to keep on moving, right? Just like the battery that we add to our digital clocks, for instance. That's one way to look at that. The battery is there to ensure that any energy that has been lost is made up by that external force. So going back here to sharing the screen. This one. Okay. We come up with the solution of this equation in the same way we came up with the solution of the other one, okay? I'm going to rewrite this equation here. So far, every solution that we have seen is an exponential function. Now, whether the exponent and the exponential function can have either an exponent that's real or can have an exponent that's complex. If the exponent is complex, if the exponent of the exponential function is complex, then we have this oscillating function that we have here. If the exponent of the exponential is real, then we have a decaying solution here. Either way, the solution is going to be an exponential. Now I want you to look at this equation here. I want to look at this equation. Without this term, the solution can be an exponential, whether it have a real exponent or a complex exponent, right? Now, if we now have this harmonic force added to the solution, okay, then remember, this harmonic function here, the sine function, is a linear combination of exponentials. Is a linear combination of exponentials of complex exponentials, right? So here you go. I can, both my sine and cosine, they can be rewritten in terms of I omega t. Here you go. Minus E minus I omega t. Over 2I. Like that. Because the sine function can also be rewritten in terms of the exponentials, so this new differential equation is going to be also a solution in terms of exponentials with a imaginary exponent. The key here now is to find out what goes inside of the exponent, okay? So what do? We try this solution here. We try a cosine solution, for instance. We could have also written down a sine solution with an amplitude that we do not know, and angular frequency times t plus a phase angle that we do not know. Okay, that's a guessing, In a way, this is a guessing game, but it's a very good guess because I am associating the previous solutions with this new one. If the previous solutions are an exponential solution, that's the argument that I'm making. And now I add a trigonometric term, a sine term, to this solution, then the solution to this new differential equation is also going to be an exponential, but with a imaginary exponent. And to make things easier, I just write it down as being cosine of omega t plus this phi angle, okay? Where omega is the angular frequency of the force. Don't forget that's the angular frequency of the force. We do know the omega, okay? In the above equation, yeah, in the above equation, omega is the angular frequency of the force, of the restoring force. We call it restoring force. This angular frequency may or may not be equal to the frequency, to the normal, there's a name for that, to the normal frequency of the oscillator, normal frequency of the oscillator, without the forced term, okay? So, go. I want this term right here. Did you get the idea? That's the most difficult part of solving these problems, is to recognize the solutions of those differential equations that look difficult. Okay? That looks difficult. What I'm going to do here, I'm going to change this y to x, okay? So I can remain consistent what I have. Instead of y, I'm going to, it's going to take a little bit of time, okay? But that's okay. You go. X, X, X. Right? X, 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 and X, 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 and X. That's my new solution. And then I'm going to take, so see what we did here? You know, I put an unknown term here. I am assuming that my solution is in terms of the angular frequency of my forced oscillator. And I add the space term that I do not know and find out whether it satisfies the solution of this equation or not. Okay, so I'm gonna bold face what I don't know. I don't know that. I do not know that. Everything else, we do not know. And then what do? We do exactly what we did before. We take the first derivative of my assumed solution. That's what I get. And take the second derivative of my guess solution, right? We have here omega square term. And then we substitute in this equation. Okay, that's my d2x dt2. d2x dt2. Here is my, I'm gonna put it on the other side so you can visualize it better. Right? And I'm going to put those two terms on the left side. So, okay. Dx, that's my dx dt. Just see here what's going on. Emma, okay, that's the second derivative. This is here. Okay, this is my kx. Okay, this is my kx. I'm going to put right here. And here is my first derivative. Okay. And we go ahead and expand all the terms. Okay, I'm going to put everything there on the other side. And we have to switch the signs as well. Here's negative, here is positive. Okay. And we go ahead and expand this cosine. It's going to be lots of work. I have done that before, and I know how difficult it is. Okay. Cosine of omega t cosine phi minus sine of omega t sine of phi. Okay. And we do the same for the other terms. Don't forget, I'm putting them on the left side. Okay, and yeah, minus. I'm gonna keep the order, the proper order that I started. It's lots of calculations. Okay. Expanding, right? Expanding, and expanding. What else do we do? Distribute everything. Okay. Distribute everything. And I'm going to put on the other side as well. Not only put on the other side, I have to change the sign. Okay. Okay, so here you go. Minus is plus is minus, minus is minus is plus. Okay. Then you have, it didn't look like, okay, I didn't change this one, right? Didn't change the order of this one. I changed the sign, but I didn't change the order. So here you go, minus, right? With plus is minus, minus is plus is minus. Plus with plus is plus, plus with minus is minus. So I just expanded it. We're going to do something else. Now I'm going to collect all those terms that has cosine omega t. That's the little trick that we use. All the terms that has cosine of omega t on one side, and all the terms that has sine of omega t on the other side. Okay, that's what I'm doing here. I'm gonna emphasize cosine of omega t, cosine of omega t, cosine of omega t. Cosine of omega t, cosine of omega t, right? 1, 2, 3. 1, 2, 3. And then everything that's sine of omega t goes to the other side. Okay. 1, 2, 3, 4. 1, 2, 3, 4. Okay. And that's what I'm doing here. Here you go. Amplitude. And I put everything under the same parentheses. I'm factoring the cosine of omega t terms. And then I'm factoring the sine of omega t terms right here. Okay, and then there's a little trick here that very few people know. Okay, so let me here write it again. Instead of one of each different side, I'm going to now here write it with everybody else in one side alone. And then what goes on the right side is going to be 0. Okay. And that's where the little trick lies. The little trick lies right in the next step. Cosines and sines of omega t are perpendicular functions, just like we have perpendicular vectors. We also have perpendicular functions. Okay. Because of that, we can make this term, this coefficient of the cosine of omega t equal to 0. That was exactly what I did. K minus omega squared cosine of phi b omega sine phi. There's no cosine omega t here, but that's the coefficient of the cosine of omega t. And then we have this coefficient of the sine of omega t. Okay. Equal to 0 as well. Remember that I told you that we have two unknowns. The unknowns are A and alpha, the amplitude and the phase angle, the phase solution. Okay, the phase solution is very easy to find. The phase solution is very easy to find. It's not difficult. All you have to do, pass the sine of phi to the other. This term here is the sine of phi to the other side, and take the tangent. That's how we find the phase angle. Okay. The other equation is a little bit more challenging. A little bit more challenging to find. We will find we have to find the amplitude. Okay. One way of doing that, right? There you go, is to divide everything by cosine of phi. This term disappears. This term with the cosine disappear. This one becomes tangent of phi, but then we still have left this one here. So we still don't have a solution. We still do not have a solution. We do not have cosine of phi. We have tangent of phi. Okay. We have tangent of phi. But then, no, we recognize, that's just one way of doing that. Okay, there's another way. I like this way here. The other way, this way, to solve that, we gotta get the tangent of phi in terms of sine divided by cosine. Okay. The tangent we already know that's equal to this term here, right? And I didn't put it there, did I? Okay, so let's do that. Replace with this term. Can we do better than that? I think so. Like that. Okay. So how can we proceed with that? Okay. One way to solve that, is just to recognize that since sine of phi divided by cosine of phi is equal to this ratio, we can also state that sine is going to be given by a constant, by a non-constant, times this numerator. Okay, this is a trick. This is a trick. I like this trick. There is another way to do that. There's another way to solve this equation. Okay, and the cosine is going to be given by the same unknown constant. Okay, multiplied by this denominator. Okay, at this very moment, C is unknown, but we can determine C by using this relation here for sines and cosines. Okay. Once we do that, go ahead, get the square of sine, which is the C square, right? Plus CB omega square equal to 1. And now we solve for our unknown. Our unknown is this value here, or plus and minus this square root, this complicated square root. And now we can finally, find out what my cosine of phi is. Okay, that's sine of phi, that's cosine of phi. Okay, and we can go ahead, plug it into our equation. Okay, and we can finally write down A in terms of what is known. We know B, we know omega, which is the frequency of my force. We know K, we know M. And then we finally get something like that. The plus and minus sign, goes to the right side. And we find out that the negative value is not a solution because your amplitude must be always positive, right? And that's the solution that we get. Okay, there's the square root here. There's this other term outside the square root, which can go inside the square root and simplify what we have downstairs, and vice versa. Don't forget we're solving for A, right? Here you go. Here's my amplitude. So let's get all the two solutions together there at the end. Okay, now we have our full solution. And we can start looking at this equation and finding out how it behaves with respect to different omega constants. Okay. What else I'm gonna do? Let's see if I have. Okay, I didn't finish that yet. What time is that? 11:15. Let's try to finish it. Okay. Oh, 11:15. What we are going to do is the following. Okay. I'm going to multiply by m and divide by m. There's a reason for that. Multiply by m and divided by m, right? No, we don't need to do that. Let's keep this way for now. What I want you to see is that this k divided by m is something that you're already familiar with. Okay, is my angular frequency. But it's not any angular frequency, it's the angular frequency of the simple harmonic oscillator. Okay, we're doing that on purpose so you can have a better visualization of what we're doing. Okay, better visualization of the equation. This mass here goes outside because it's being raised by the second power. We have to raise by the second power as well. And then what else do we do? We multiply. This is a mathematical trick that we use to make the equation look better. Okay. We multiply and divide by m squared as well. When we do that, we can put this m squared in evidence, those two m squared in evidence. Okay, and that's what's going to be the next step. Okay, so Emma, okay, and I'm going to put the B omega Emma, and then we square here. Okay. What we do next? Remember the right? The omega here is related to that angular constant of the simple harmonic oscillator. Angular frequency of the simple harmonic oscillator. Okay. So now it's easier to interpret that these results. Okay. Plotting A versus omega. Okay. No, not plotting. Let's say A has a maximum value. You don't even have to plot it. Just looking at the equation, right? Has a maximum value whenever equal to 0. This term is equal to 0. Let's see here. I have omega square here. Oh yeah, there's a, okay, I forgot to square here this term. Okay, this one is not omega naught. This one is omega naught square. Okay, omega naught square. Oh, not this one. Omega naught square. You go. Omega naught square. A has a maximum value whenever this term is equal to 0. Do you believe that? Right? If this term is not 0, this term will end up adding to this other term that's positive. And the amplitude is going to decrease. But the maximum amplitude, so the maximum amplitude is going to occur whenever the frequency of your force, angular, or the angular frequency of your force coincides with the frequency of the simple harmonic oscillator. Okay. And it's possible to make some neat plots of that. And I'm going to show you, some plots when we come back from the break. Okay. So that's 11:25, right? AM. Let's have our break until, until 11:40. Then we go just for 20 minutes.
Professor.
Class. Okay.
Hello.
Any questions before we?
I have one.
Yeah, go ahead.
I know that you took roll in the beginning of the class,
Yeah.
but there was, I know I came in like 2 or 3 minutes late. I don't know if you marked us here.
Yeah, you are Alex, right?
Alex Hernandez, yeah.
Alex Hernandez. Oh, okay, here you go. I put a.
Yeah, I know that a couple of other fellow peers also got here a little bit
Are
late.
there any other students who arrived late? Are there any other? Let's see, we have 9. There must be one more student. Is that Jeshu? Who's beginning? Jeshu. Okay, Jeshu. Okay, Jeshu is here. Sartak, right? Maybe Sartak. Yeah, it's Sartak. Sartak, are you there? Okay, I'm gonna put a star here. Is that Sartak or Kartika? I cannot hear you. Okay, if you may please type there in the chat box. Oh yeah, here you go. Thank you. Okay, thank you. So here you go. Now we have the right number of students and 11:25. So I see you in 15 minutes. Okay. Yeah. Ya que a gente vai saber. Não, I'm back here. And let me share my screen. And now that you have the amplitude here, let's not forget, this formula was derived for whenever you have damping in the system, right? And initially it looks very difficult to see this formula, but once you plot it and carefully look at that, remember, F naught is constant, mass is constant, B is constant, right? What if we can, and omega naught is going to be constant too, because it depends on K and M. On K and M, right? That's the natural angular frequency of the single harmonic oscillator. That's what we call it. Omega naught is, I'm gonna write that down here. Omega naught is the natural. Omega naught is called the natural. The natural angular frequency of the simple harmonic oscillator. And the closer the frequency of the force is to omega naught, the higher the amplitude. That's what you have to know. The closer this frequency is, the closer this value becomes to 0. And the smaller becomes this denominator. When we plot this equation here for different values, we get this genetic behavior. This behavior that you're going to see is a genetic behavior, not just for those specific values. I put here for mass 2 kilograms, K 4 newtons per meter, omega naught, which is K divided by mass, and the square root of that is giving me 4.47 radians per second. I used the force, amplitude of the force of 6 newtons, and I used a damping coefficient of 0.1. Okay, so when we plot that for different values of the angular oscillation of the force, right? Omega is not necessarily equal to omega naught, remember? We get this type of behavior right here. Okay, that's the amplitude. That's the amplitude of your oscillator, of your forced oscillator. We end up getting a peak exactly at 4.5. It shows here 4.5, but in reality it's 4.47. That's where the peak is. That's where the peak lies. The maximum amplitude that we get is this 9 meters. Okay, 9 meters. Then it all depends, of course, on the parameters, right? So what if we have more damping? If we have more damping, we should expect a lower amplitude, right? Yeah, that's exactly what we get. From 9, you get to 6. The larger the damping, from 6 to approximately 4, right? And so on. What about 0.5? I'm gonna put 1, okay? That's the behavior. It's not a symmetric curve. You can see that this side here is not symmetric with respect to this side. It starts to become symmetric when the damping coefficient starts to behave in a symmetric fashion, when the damping coefficient becomes very small, just like we have here. And again, we get the most amplitude whenever the angular frequency of the force matches the natural angular frequency of your oscillator, right? Let's do that. Here you go. 1, 2, and so on. We have a similar phenomenon like that for circuits. There are some circuits out there that behave just like that. Okay, there are some circuits out there that behave exactly like that, and that is the you know, when the two frequencies matches, that's the resonant point, the point of resonance, okay, between the force and the natural frequency of the oscillator. When B is equal to 0, okay, then you do not have any damping whatsoever, and in theory, this thing should go to infinity. The graph is showing only 14, but in reality, if you do omega for exactly 4.47, this amplitude should go sky high. Okay, should go sky high, and it's 4.5 here, right? Here. 4.5. That's the maximum amplitude I'm getting. But if you 4.47, right? 47 is going to be even higher. See, 157. And that's because I'm not exactly at resonance. If I get closer and closer to resonance, this number becomes larger and larger. 4.472136. Okay, now it's a number that 7 million, right? It's still not infinity, but at that exact point is going to be infinity. And that's because I put a B value equal to 0. Okay, 0.1, let's see, 0.1, yeah, notice that it doesn't change much as we get closer and closer to the resonance point. From 8, it goes to 13.37 and 13.41, right? And the equations is all written down here. D2 is the force, right? The square root, A2 is the mass, and so on. Everything is here. And I vary omega from 0 to whatever I have here, whatever values I have here. That's what I want to show you. And see, I'm going to put, I want to put it 1 here so you can see better. Yeah, a better behavior. And I'm going to copy and paste this graph on the notes. Don't forget it. Don't forget the amplitude of the oscillation is not the regular position. Okay. Plot of A versus omega. The angular frequency of the force, the angular frequency of the force, right? And that's what I want to cover. Let's take a look at the book. We still have, let's see, 11:51. Still have until 2 o'clock, right? Let's go until 12:15, and then we have our half-hour break. I want to go to Wiley Plus. I'll show you what we have in there, in the book. Physics 39. Launch textbook. We go at chapter 15. 15, simple harmonic motion, energy in simple harmonic motion. We did that, angular simple harmonic oscillator. Oh, that's another oscillator. Okay, I didn't do this one, but the solution is similar. This one is a device that uses torsion. So it is suspended by a wire exactly at the center of mass of this disk. This disk has a mass. This wire can be, you can provide a torsion to this wire. Can you picture that? Okay. Take this disk out of the equilibrium position and let it oscillating. It's going to, it's going to twist back and forth. It's going to twist back and forth. That's what this problem is all about. So you can put that pendulum in circular motion. There's a relationship between pendulum and circular motion. Okay. The pendulum itself describes a circular motion, a circular arc, not a circular motion, but a circular arc, right? And because of the circular arc, the distance from the point of rotation is going to be constant. Okay, we did that. Damped simple harmonic motion. Okay. Stephanie asking if you are changing the lab days. What I mentioned at the beginning, in case you're here, right? Here you go. I rescheduled the lab. We're not going to have lab this week. Okay. We're not going to have lab this week. We're not going to have lab this week because there are several students that are still taking final exams at the UC system. So what I did, I postponed the lab, the first lab for next week. Okay. It's not going to be necessarily Monday and Thursdays, but it can be consecutive days.
Okay, because yesterday you mentioned how you were going to change it to Mondays and Thursdays, so you're not doing that anymore. You're just gonna.
Only for the first few weeks, we were going to do Monday and Thursdays if we had everybody here. But I have several students that are still taking final exams. They asked it. I didn't want to,
Okay.
Didn't want to. So I decided to start the labs next week until we catch up, and then, then here you go. It's not going to be necessarily Monday and Thursdays. Okay, it's all going to depend when we schedule the exams too, because sometimes the student asks to change the date of the exam too. So just keep that for now. Lab 1 and 2 are scheduled for Tuesday and Wednesday next week, and then don't forget Thursday we have our exam, our first exam. It's going to be very hectic. Okay, I want to do the exam on Thursday. And then we're going to have exams every Thursday. Every Thursday. Okay. The difference here, the final is going to be the last day of class. This one is going to be 8 a.m. to 10 a.m. I want to do those exams 12 to noon. Okay. I want to do those exams 12 to noon. Noon to 2. Noon to 2 p.m. 12 to 2. 2-hour exam. So far, we have chapters 15, 16, and 17 scheduled. We already finished section 15. And let's go back to the book again. Go. Damped simple harmonic motion, right? And forced oscillations. Here you go. That's one example of damped simple harmonic motion. You can have, instead of having the mass completely submerged, you just attach something else to the mass, and this vein ends up submerged in water. There are practical devices out there that use this type of motion, right? Like those things that we put in the doors, right? So the door doesn't oscillate back and forth. It's a damper device. Most classrooms have this device in there. Okay, here you go. Here's the oscillations that are being damped. just like the drawing that I made, you know, the upper exponential decay, the lower exponential decay, the envelope, the upper envelope and the lower envelope. Forced oscillations at resonance. Okay, here you go. Here's a plot from the book, very similar to mine. The higher, the larger the damping effect, the lower the amplitude, provided everything else is the same. Provided everything else. Notice that they put a ratio of the WD, omega D is the what I call omega, is the angular frequency of the driving force, okay? And omega is just the regular square root of K over M. I call that omega naught. In my notes, I call this one omega naught. In my notes, I call this one omega. Okay, and here's an example of a forced oscillation during an earthquake. Intermediate height collapse in Mexico City in 1985. Look here. I was there in Puerto Rico and something like that happened. And people start talking about that. Buildings of intermediate height collapsed in Mexico City. I was talking to some civil engineers there at the university at the time. And it was surprising. They were surprised that buildings, you know, not the tall buildings they collapsed, but the buildings of intermediate height collapsed. Taller and shorter buildings remained standing. But all it has to do is forced oscillations, which have to do with the angular oscillation of the natural angular oscillation of the building, which must have matched the frequency of the earthquake, of the wave of the earthquake. And that's what we have for this chapter. Okay. Those are the homework, the questions, right? And so let's write down the sections. We're done with chapter 15. And we covered everything. 15.1 to 15.6, okay? Sections 15-1 through 15-6. 15-6. And what I want to do now is to start chapter 16. Let's go for 15 minutes. And then we have our half-hour break. So everybody can get something to eat, right? Wave motion. And I'm going to get this thing out of here. Later we can edit that with all of this stuff here. Okay, that's where I want to start. Waves. Everything else, that's page number. By the way, I gotta do something here. Yeah, I gotta I always like to. Oh, I clicked the wrong place. Go. Right in here. We gotta put a page number here. Insert. Okay, 24. Now we have the right page. We have what we want. I'm gonna do waves now. Okay, the best way to understand a wave is through examples. Okay. And we start with examples of mechanical waves, and then we extend this example of mechanical waves to other types of waves that are not so obvious, okay? Mechanical waves are very easy to visualize. All you have to do is to have a string. Everybody's familiar with that. Apply a disturbance to that string, and you see a pulse propagating through this string. Okay, and it's amazing that this type of phenomenon occurs under other circumstances as well that we cannot visualize. Water waves can also be visualized, right? You apply a disturbance to the surface of a pond, and we see this wave propagating on the surface of the pond, on the surface of the water. So waves that can be visualized. Let's put this way. Here you go. Yeah, mechanical waves in a string. Water waves. Waves that cannot be visualized. Sound waves. We cannot see sound waves. We can hear sound waves here. But we hardly know that it is a type of wave. Yeah, it is a type of wave. And then we have electromagnetic waves. Light, radio waves, microwaves, UV, infrared, X-ray, gamma rays, etc. And not just sound waves that we can hear, but also ultrasound and infrasound waves. It was very similar to sound waves. It just happened that we cannot hear them. There are all sorts of waves out there. Okay. So there is a very close relation between a wave and a source of vibration. Okay, to create a wave, you must have a source of vibration. To create a train, even better, to create a train of waves, you must have a source of vibration. So just try to see when, remember when you get a string, right? The string, you have the one end in your hand and the other end attached. If you keep on moving it up and down in an oscillatory fashion, you're going to see this train of waves propagating away from your hand. What actually is propagating is energy. Energy is propagating from your hand away from your hand. Okay. So we can state that oscillations generate a wave. An oscillation can generate a wave. By the same token that oscillations have a frequency, okay? Because an oscillation has a frequency, its associated waves also, even better, also will have a frequency. We have a frequency. Not just we'll have a frequency, but we'll have the same frequency Okay, number of oscillations per second. Can you picture that? Oscillations also have an amplitude. And waves also have an amplitude. If the medium doesn't change, the amplitude of the wave is going to be the same amplitude of the oscillation. Okay. And a wave that, because an oscillation has a frequency, has the same frequency, because since the wave has the same frequency of an oscillation, the wave is going to have the same period of the oscillation as well. Then we have two other things that we don't see in an oscillation. A wave has a velocity. An oscillation doesn't have a velocity. A wave also has what we call a wavelength. And I'm going to cover that with you, which is the distance between crests, okay? So a wave has everything that an oscillation has and more. That's why we study oscillations before we study a wave. So here you go. Let me get, see if I can find my own. I have a nice simulation about waves. Well, okay, so that's the most important type of wave. Is a sinusoidal wave. We can see those things in strings. Okay. At a given instant, this is a snapshot of what a sinusoidal wave looks like. A sinusoidal wave is also described as a planar wave. Can you remember that? Every time we talk about a planar wave, the wave itself has this sinusoidal pattern along its length. So try to visualize your string. Okay, at a given instant of time, you're oscillating your string, and at a given instant of time, you take a snapshot of your string, and the string looks just like that, as a wave that's propagating from the left to the right. Okay, note that I have here, why do I put y? Let's take a look there at my equation, right before. Right here, did you notice that I wrote down my wave as a function of x and t? Okay, that's exactly what I see in here. We have y along the vertical axis and x along the horizontal axis. That's the position along the wave. And then this wave at a given instant of time t. For this specific case, the instant of time t is 3 seconds. Okay, but even more important, it's not just any f, it's not just any function of t for that specific wave. F of t is going to be either a sine or a cosine. Okay. A generic way of describe a wave is by using this notation here, a function of x and t. But again, just like I said before, the most important types of waves are those that are in terms of sines and cosines. Those waves in terms of sine and cosine are called planar waves. Waves, waves in terms that waves that have a functional relation, that have a functional relation in terms of sines and cosines are called planar waves. Here's a planar wave. And the planar wave must be a function of x and t. Now, the next question is, which is specific relation between x and t, okay? Which is specific. Every, all the waves that we're going to study here in this chapter is going to be a wave that will have a relation like x minus vt or x plus vt, okay? It doesn't, like I said, doesn't necessarily have to be a sign, it can be other things. And why x minus vt, okay? Well, because every function that behaves this way, that has a functional dependence of x minus vt, is a wave that propagates to the right, that moves to the right, wave that moves to the right. And every wave that has this functional relation x plus vt is a wave that moves to the left. Can you remember that? The negative sign indicates a forward propagating wave. A positive sign indicates a negative propagating wave. It's possible to see that through simulations. Okay? And there are other ways to see that, but the most fun way of seeing that is through simulations like this one here in Excel, okay? So here you go, we have the number of data points here, right? I put n equal to 0. And I made my x equal to 2 pi times those integral numbers. That's what I'm doing here. 2 pi divide by 61. Okay, divided by 61. I choose 61 so I can get enough data points in my wave. And here, what I did, I wrote down my wave, my planar wave, in terms of amplitude. 0.4 meters. See the amplitude of 0.4 meters here? Remember, this guy is an oscillator, right? That has this amplitude of 0.4 meters. It's oscillating back and forth, and this oscillator is attached to the string and generate a wave. Can you picture that? Okay. The x minus vt is right in here. B2 is Vx. G2 is V. H2 is T. H2 is T. Let's see here. Oh, I did something I'm not supposed to do. Let's see. Oh yeah, this one. Okay. Okay, we're in good shape here. So I'm gonna put here time t equal to 0. So you're gonna see how my wave looks like. Cosine, don't forget v x minus vt is here inside it. Then you have to have a normalizing term to ensure that this whole expression inside the cosine is going to have no dimension whatsoever. What we see here is 2 pi over f2. F2 is what we call the wavelengths of my wave. Okay, so that's how the wave looks like at time t equal to 0. At time t equal to 0, we have maximum amplitude at x equal to 0, right? There's a cosine, and the distance between those two peaks is what we call the wavelengths. I can adjust the wavelengths of my wave just by changing the wavelengths here. Oh, in this expression, I want to make it shorter. Let's say 7. Okay, I made my wavelength shorter. I want to make it longer. Okay, I made my wavelength longer, 20 meters from here to here. The genetic expression for this wave is the following. It's given right in here. You already know that we must have an x minus vt parameter. That's going to be our forward propagating wave. But this term here, because it has a dimension of meters, it must be divided by another term that has a dimension of meters. And this term ends up being the lambda, the wavelengths. And you got to go at 2 pi over lambda, okay? That's what we have in there. And there's another way of writing that expression. Okay, I can move this 2 pi over lambda to the inside, 2 pi over lambda here. This 2 pi over lambda term has a name. Oh boy, we usually call it a K. Okay, it's not the K for the spring constant. The K in the above expression is not the same. Oh, it's not the same K for the spring constant. We're just using, we're just using the same symbol for two different things. We are just using the same symbol for two different things. This K is called the wave number. We have the wavelength, and then we have the wave number. And we don't have this negative, this positive here. We have a negative here. We're supposed to have a negative here. What you end up getting here is going to be a term that we call the angular frequency of the wave. Okay, the angular frequency of the wave. Let's take a look at our simulation and see if the wave really propagates from the left to the right. Remember, I put a minus sign here, right? I put a minus sign here. I'm going to bold face it. And we have this wave at t equal to 0. Let's put 0.5 here. Yeah, do you see it moving a little bit to the right? Now, around 1 second, a little bit more to the right, 1.5, 2, right? 2.5, and so on. There are other ways to visualize this wave propagating to the right. Okay, now I'm going to go in larger and larger steps. Okay, 7, 8, 9. Okay, and then I'm going to undo it. You can see the wave is going back in time, right? Until we get to 0. And now I'm going to go forward again. Play the movie for you. Half second, 1 second, 1.5, and so on. Do you see the wave propagating to the right? Right? That's a forward propagating wave. If we put the wave propagating, if we put a positive sign here, then we're going to see the wave propagating to the left instead. A backward propagating wave. Okay, time t equal to 0. Oh, not here. Time t equal to 0. All right. 1, 2, 3, 4. See the wave propagating to the left. 5, 6, 7, 8, 9, 10. Okay. And now I undo everything. You see the wave propagating to the right because I'm going back in time, and then I'm gonna go forward in time again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Remember that. It's possible to prove mathematically that a function of x minus vt is gonna move to the right as time goes by, and f of x plus vt is going to move to the left, like you're seeing here. It's possible to prove that mathematically. Okay. Okay. this wave that you see right in here in my simulation is we call it a transverse wave. We call it a transverse wave because the wave propagates to the right and the amplitude, varies in a direction perpendicular to the direction of propagation. Okay, the disturbance is moving up and down here while the wave propagates to the right. Okay, so 12:24 now, right? Let's see when we finish was our last break. 11:40. Yeah, I think that we can stop now, have another half-hour break so we can eat something, right? And any questions about that? 12:24. So in summary, waves are generated by oscillations. We have all sorts of waves. The most important waves are the planar waves that are given in terms of sines and cosines. That's a planar wave. On the top of that, you can have any type of wave, any functional form of wave. And these waves are described by this function in terms of x and t. There are waves that propagate to the right, forward propagating waves. Those waves have this functional dependence in x and vt, x minus vt. And then there are waves propagate to the left that has this functional dependence of x plus vt. That's what you have to remember. In addition to that, waves also have a velocity and a wavelength, in addition to the frequency, amplitude, and period that are afforded for oscillations. So let's have our break right now and break between 12:25. Any questions before you go to the break? To 12:55. Okay. Yeah. So I see you shortly. Okay, so we are back here, and so let's just summarize what we have talked about waves. Okay. Okay, so waves have a genetic relation that's given by something like that. Y is just the distance from the x-axis. And a wave is a function of two variables, x and t. Strictly speaking, a wave has this type of functional relation. Okay, strictly speaking. And a wave that has this relation is a forward propagating wave. Okay. And a wave that has this type of relation is a backward propagating wave. The most important type of waves, are planar waves given by either a sine or cosine. Either sine or cosine, okay? This is a forward propagating wave. And I'm even going to put plus and minus here. any wave can be written as a combination of different planar waves. That's why those planar waves are so important, because any other wave that is out there can be written in terms of this type of wave here. Okay. What else do you have to know? Huh? You have to know that a wave has a frequency and a period. We already mentioned that, but we're mentioning it again. Okay, a wave, like an oscillation, has an amplitude. Oops. Frequency and period. And what oscillations do not have? You know, but a wave, unlike an oscillation, has a speed. A wave, unlike an oscillation, has a speed, and it also have a wavelength. Okay, wavelength is distance from crest to crest. And what about the speed of a wave? Okay, the speed of a wave is very simple. You know, the speed of wave is given by the wavelength of a wave divided by the period. And it makes sense. Okay, it makes sense. Why is that? It makes sense that it's given by that. Okay, if we're talking about this type of wave here, okay, what is the period? The period is an oscillation that goes down, up, and down, right? That's what the period is. It's an oscillation that goes down, up, and down back to the initial points. During this period, what's happening? You know, the point that was here has moved this distance here, right? Make sense? The point that was initially here moved this distance, and this distance happens to be the wavelength, which is also this distance from crest to crest. From crest to crest, or from every other node. There's a crest, that's a node, okay? And that's a valley. From crest to crest, from valley to valley, or from every other node. Can you remember that? Every wave has this relation. Lambda divided by t. This is a generic relation. This is a generic relation for any wave, okay? For any wave, whether it's a mechanical wave, whether it's a sound wave, whether it's an electromagnetic wave, okay? Whether it is a wave in a string, a water wave, a sound wave, an electromagnetic wave, etc. That's what I mean by generic.
Professor, just one quick question. Sorry to interrupt. So for the velocity, you're saying that that's not velocity of like that we're like what is it, meters over over time. This is the phase velocity, correct?
Well, for first it's not velocity, right? It's speed. Okay.
Yeah, it's just speed.
Okay. Yeah, it is meters per second. Yes, it is meters per second. And
oh, it is meters per second.
Yeah, it is in meters per second. And
oh, okay.
Okay.
I was just trying to make sure I understood it correctly. Thank you.
Yeah, but remember, there are two velocities here in this wave. I didn't get to this point yet, but there are two velocities here. there is the velocity of each material point in the wave, right? I didn't mention that. The velocity of each material point or wave that I didn't mention before is the velocity of each point going up and down, okay? The velocity of the wave is something else. The velocity of wave is the horizontal, is the velocity of propagation of the disturbance along the wave, okay? And that's what is lambda divided by t. Now, the velocity of each point going up and down here is we're going to calculate later on, okay?
Thank you, Professor.
Okay, so let's put that here. Let's write that down here. So not velocity, right? The speed. There are, there are two different speeds, right? Speeds. The speed of the wave or the disturbance, right? Disturbance that propagates along the wave, okay? Which is also the speed of the energy that propagates along the wave, and the speed of each material point along the medium, okay? In the case of a transverse wave, this speed is along the vertical direction, whereas the speed of the wave is along the horizontal direction. See the difference here? Okay. Period and wavelength. So the core parameters of the wave, okay, the core parameters of the wave are, one, amplitude, period, and only three wavelengths. Everything else comes from those three. I would say the primary definitions, right? The primary parameters of a wave, And then we have the secondary parameters, the secondary parameter definition. Secondary parameters are the speed, right? Which is lambda divided by v, the speed v. The frequency, which is 1 divided by t. Wave number is also another secondary parameter, wave number. Where it's 2 pi over lambda. Can you remember that? Sometimes there's a lot of things, right? But before you dwell in everything that's secondary, just remember what's primary. Okay, those three. That's what you have to concentrate. And then you also have the angular frequency. Right? The angular frequency is the omega 2 pi f. Okay. And then you have to decide for yourself, what do you think is easier? It's easier to memorize this equation here, right? It's easier to memorize this equation? No, decide by yourself. What is easier to do? To memorize this equation? The equation below? Or memorize the other one that we saw, right? The other one that we saw was this one here. Kx omega t. Okay, this v here, remember, it's going to be lambda divided by t, right? Lambda is going to cancel its lambda. 1 divided by t is the frequency, so you're left with the omega. Let's do that step by step. There you go, this one here is going to be lambda divided by t. Oops. Lambda cancel out this lambda. We end up with 1 divided by t. 1 divided by t is the frequency. And we finally get 2 pi f, which is omega t, omega. For me, I prefer this one here. I prefer this one here. I prefer this one because we have the x plus and minus vt, right? And then I know that this guy here has a units of meters, so it's natural to recognize that you must have something with meters downstairs, and then you have to have this 2 pi radians upstairs to keep track where the position of your wave is. Okay. Now we can start talking about the vertical velocity of the points of the medium, right? Now let us talk about the vertical velocity of the points in the medium, in the propagating medium. The string is just a propagation medium, is a medium of propagation, propagating medium. And the wave propagates in this medium. This velocity v sub y is going to be given by, no, I gotta get this one here, dy, this is a partial derivative, right? Partial derivative. We have to have a partial derivative because this y is a function of both x and t. X and t are independent variables. Did I put that? I'm forgetting here the amplitude, right? Let's put the amplitude back there. Yeah, I'm forgetting the amplitude here. Let's put the amplitude back there. Amplitude back here. Amplitude. The amplitude is constant, so you don't have to worry about it. Amplitude. Amplitude. One student coming. And now we are going to take the partial derivative of this cosine. Okay, and when we take the partial derivative here, cosine becomes minus sine, right? And then we have to take And then we have to take the partial derivative of the argument of the function. Chain rule. Partial derivative of x is going to be 0. So we are left with the omega t. We are left with plus and minus omega t. Minus and we are left with plus and minus omega without the t. Let's go one more step. And then it becomes minus and plus. Okay, minus and plus omega. That's going to be. So this velocity, this vertical component of the velocity of the points of the wave, of the points of the medium, change as time goes by. It's a more complicated type of motion. But the maximum value okay, the magnitude of this maximum value, is just omega A. We can also talk about the acceleration of those points of the wave. Of the acceleration of those points of the medium, not of the wave. Okay. And that's going to be like that. Next line here. Right, like that. One more. Oh, everything that's a constant can go outside. And then we have to worry about differentiating the function, which is going to be cosine. We're going back to cosine. And then the argument of the cosine. Okay, and then we end up with plus and minus omega here inside the parentheses. I'll put it right in here. Yeah. Note, see that we have a different order, right? Here's plus and minus, here is minus and plus. do it right. Let's see if I did it right. Okay, so second derivative, let's minus and plus, right? Yeah, yeah, it looks like I did minus and plus, right? We got the cosine, there is no negative whatsoever, and then it becomes plus and minus. Yeah, okay. So when we get plus and minus multiplied with minus and plus, we get minus omega squared. Okay. So just like we did before, what's going to be the maximum acceleration in the vertical direction? Maximum acceleration in the vertical direction is going to be omega squared times the amplitude of your wave. Okay. Omega squared. We have 120 already. And then we started. Let's see here. 12:55, right? So let's see if we can go until the very end without a break. Okay, so I'm talking, I told you that we have all sorts of waves, right? But planar waves are the most important ones. They're in terms of circular function, but we still can define other types of waves, such as like a triangular wave. A triangular wave is like just a straight line, a times x minus vt. It's a straight line that moves from the left to the right. That's one type of triangular wave. And then we have this other triangular wave that moves. This one moves to the right, this one moves to the left. We have the exponential wave. We can define an exponential wave as well. You know, a constant time x minus vt, and so on, okay? And we did that. So what we're going to do now, you know, it's also, remember, now we're going to talk about the speed of wave. In a specific medium. Okay. Remember that the genetic equation for the speed of a wave is what we saw before. It's lambda divided by t. But what about an equation for the wave in terms, not in terms of the parameters of the wave, but in terms of the parameters of the medium, okay? For instance, right? For instance, a wave propagating along a string, the speed, for instance, the speed of a wave propagated along a string can also be written in terms of the parameters of the medium itself, and not the parameters of the wave, instead of the parameters of the wave, okay? And it's possible to do that. For instance, it's possible to do that for a medium being the string. It's possible to do that for a medium being the air, okay? And what you're going to get is not going to be lambda divided by t. It's going to be lambda, it's going to be something else that is a function just of the parameters of the medium. I'm going to give you an example, okay? We can prove that, but we're not going to do that because it takes too long time, okay? Let's see if I have an illustration here. Okay, here we go. Here's another type of wave, and I'm going to cover that. Okay, here you go. Here we have the case of a string. Okay, and this string, we can put an oscillator there in this string. No, not that. We can put an oscillator, for instance, at the end of the string, or you can just plug this guy here, and you're going to generate that wave that we are familiar in that we all see in a guitar, right? In the strings of a guitar. So what's happening here? We are having, in this case, we have a wave here that's going to depend not only of the inertia of the string, which is related to the mass of the string, but it's also going to depend on the force applied by this weight here at the end of the string, or the tension in the string. Can you picture that? And it's not difficult to memorize a relationship for that. Okay? For a string like this one, okay, the speed of the wave in terms of the parameter of the medium, we're going to write like that, is a function of the mass of the string, of the length of the string, but it's also a function of the tension that the string is applied to. Does it make sense? And then I'm going to go even further. The mass is a parameter that depends on the inertia of the string. Okay? Consequently, it's natural to presume that the speed must be a function of the inverse of something that's the inverse of the mass, and something that's not just the inverse of the mass, but directly proportional to the tension, the force that applies to the wave, that is applied to the wave. Okay? When we do all the mathematical calculations of that, see, those are the parameters of the string, right? Of the medium. There is no lambda there. There's no wavelengths there. There's no period there, right? And when we do the proper mathematical calculations, what we find? We find out that the speed of a wave in a string is going to be, I want the square root here, okay? Going to be something like that. The tension that you apply divided by the mass of the string, but it's not just the mass, it's going to be the mass divided by the length of the string itself, okay? So in a way, it's directly proportional, the speed is directly proportional to the length of the string. But don't forget, we have a square root here. We can go a step further and write that down, that instead of mass divided by length, what we write down here is the linear mass density, where T is the tension in the string, and nu is the linear mass density of the string, or M over L. Okay. Can you picture that? The larger the mass of the string, the more inertia it has. So it's going to slow down your wave. The larger the force applied to the string, the larger the tension applied to the string, is going to speed up your wave. But there is a square root here. And there is a step-by-step solution for that. I'm going just to spell that out for you, but I'm not going to do the derivation itself. Okay. To calculate that, the steps to prove that, not calculate, but to prove that the steps are the following. 1. Okay, first you have to illustrate the string and the wave propagating along the string. Let me bring down the 11, right? Good. Okay, and the wave propagating along the string. Consider an infinitesimal mass, delta m, of the string. I will put that here in a better way, delta. String. Determine the forces applied to this infinitesimal mass. That's the tension. And consider the arc of the string, an arc of the string, right? Approximate. Remember, it's a wave, right? It's roughly sinusoidal. Approximate an arc of this string. Of this string is as a circular section of radius r in length approximately delta s. Why delta s equal to delta x? There's a reason for that. Delta s approximately delta x. Delta x. Okay, this is a statement. This is a statement that the disturbance on the string is very small, and for this reason, the arc is very small in along the vertical direction, right? Along the vertical direction. And for this reason, the arc, along the vertical direction, I mean delta y. Delta y. And for this reason, the arc length should be almost the horizontal component of the string, okay? And then when we do that, we apply Newton's law. In this case, we are saying that the arc of the string is approximately a circle of radius r. So we apply Newton's second law, which is the centripetal force must be equal to mass delta m times the centripetal acceleration. Okay. Net force is equal to the vertical component of the tension, which makes a small angle with the horizontal. The horizontal component cancels out. And the acceleration of this arc. Those are the steps that you have to take. So when you do all of that, you get something like that. Okay. This v here comes from the centripetal the velocity on the centripetal acceleration. Okay, that's why we have a square root here. If you pass the square root to the other side, notice that you're going to have a square here. See that? If you pass the mu there to the other side, you're going to have m in there, right? M over L. Okay. And that's more or less it is derived. Okay, 135 right now. Oh, we're more, okay, 25 minutes more to go. If you want to take a closer look, I have here everything in my notes. We also have that in the book, okay? We also have that in the book. Here go the net force applied to that infinitesimal length of the string is going to be twice the vertical component of the tension, because you have two tensions pointing downwards. We have a sine of theta there. Delta m is the mass times the acceleration. Okay, because the angle is very small because we have very small displacements from the equilibrium position. The arc of the string can be modeled as a small section of the arc of the string can be modeled as though it's making arc of a circle. For this reason, the acceleration is v squared over r, where the r is the radius of that infinitesimal arc of circle. Sine of theta is approximated to theta. Okay. And then you combine the r with theta. That's going to be a length, the length of the string. And this 2 here, you know, is going to be related to delta x and r theta. That's the quick brush on how that thing is derived. Okay, but the best way to do is to memorize it as in terms of the force applied to the string, which is to the medium of the string, which is a tension. This tension should be directly proportional to the velocity because it helps on the speed of the wave, and is inversely proportional to the mass, linear mass density, to the inertia of the string. Okay. In the first lab that we do, we use this equation here. And by the way, because that other equation that you see here is a genetic equation, you know, what you see right in here must be equal to, and here you go. Now I have to change my parameters, right? This t here I shouldn't be using t. I should be using, I shouldn't be using tension as t. Let's see, I'm going to change it. I want to put F, okay? F for force. But this force is a tension. You know, put a lower subscript t there, so you know that the tension force, so you do not mix up with the t for the period. Okay. And let's not forget this thing is an approximation, okay? I'm going to emphasize that. No, you know what? I'm going to put it this way. The approximation is right in here. The approximation is right in here. And because this thing is an approximation, we should have an approximate sign here as well. Lambda over t. Okay. 138. Any questions so far? That's lots of things, right, to cover. Then, in addition to this string here, to the speed of the string, there are other equations that you can derive for different waves, for different medium, right? In the case of the electromagnetic wave, for instance, we can determine, a much simpler equation for the speed of the electromagnetic wave, and that comes, which is going to be something like that. If you already taken electricity and magnetism, it's going to be epsilon naught, and then what goes mu naught. Okay, going to be something like that. For an electromagnetic wave, which also going to be equal to lambda over t. In this case, it's not going to be an approximation. It's going to be exact. Okay. For an electromagnetic wave, we have something similar. For an electromagnetic wave, we have the following, and we can derive that. This one I'm going to derive, not now, but we have the following relation for the speed of the wave. Epsilon naught, epsilon naught is a electric constant, right? And this one here is the magnetic constant. Okay, this one doesn't belong here. This one belongs here. Huh? What's going on here? Let's see what I did here. Uh-oh, looks like I have to redo it again. Okay, here you go. The period. That should belong right here. And we have 20 more minutes to go. Do you get the idea? Okay, this is the genetic relation for any wave. But then when you go specifically to certain waves, you have to consider the medium that they are propagating, the parameters of the medium that the wave is propagating. In the case of string, the parameters are related to the linear mass density and the tension in the string. For electromagnetic wave, the parameters are related to the medium that the electromagnetic wave propagates, which is the vacuum. The vacuum has those constants associated with that, epsilon naught and mu naught. If it's not a vacuum, if it's something else, like glass or plastic, it should be related to those electric and magnetic parameters of the medium itself. Okay, and then we have other types of medium as well, like the water waves and so on. Okay, the next thing that I want to do is going to be the wave equation. The wave equation. A very important equation to keep in mind. Is a partial derivative equation, a partial differential equation. And it looks just like that. Okay. It's going to be it's possible, it's possible to derive this equation. It's possible to derive this equation. But the process is lengthy as well. So how do you come up with the solution of a wave, right? What's the starting point of a wave? Okay, the starting point of a wave is this one that you see right in here. It's a partial differential equation. And the partial differential equation in terms of time and in terms of the position. You know, if you remember that, you can remember the rest. You can remember the rest. Here we have length divided by time square. M divided by meters per second square. And here we have length divided by length square. If you remember that one is proportional to the other, it's just a matter of figuring out what is the constant that goes in front of it. Okay? You just do dimensional analysis, and that's what I'm doing here. That's a very nice way to memorize the wave equation. The first step is a second partial derivative of y. One partial derivative, second order partial derivative. One of the partial derivatives is second order in t. The other partial derivative is second order in x. And by the way, this is the case of a 1D wave. 1D wave. One-dimensional wave. There must be a constant here, because those two partial derivatives are proportional to each other. And then we're going to find out what is constant just by doing dimensional analysis. The left side is meters per second squared. The right side, this guy here, is meter divided by meter square, or 1 divided by meter. So this constant that you see right in here must have a dimension that is going to be the dimension of the velocity square. Okay? And just by doing this simple analysis, we can easily memorize the equation, the wave equation, as being something like that, proportional to v squared. V is the velocity of the wave. Okay, that's another way of writing it. Okay, that's a 2D wave. We also have 2D waves out there, not just 1D waves. Okay, and now what I want you to do is to prove that this relation here satisfies this partial derivative equation. Okay, let's do that together. Okay, prove that both waves here. I don't want prime here. I'm going to put backwards, E for backwards, okay? Backward propagating wave. Prove that both solutions that you see right here is a solution for the one-dimensional wave equation. Let's do the one-dimensional wave equation, it's easier. Okay, so how do we do? Okay, we start just by differentiating y with respect to x. I'm even gonna do, you know, okay, like that. And I will call, try to do that yourself too. I will call this x plus and minus vt, or minus and plus vt, as a parameter u. Okay, where u is a function of x and t. Then we have to use our partial derivatives, our knowledge of partial derivatives. We're going to use the chain rule. So what do we do? Total derivative of f with respect to u, chain rule du dx, right? But du dx is going to be 1. partial derivative of u with respect to x is going to be 1, right? That's why I end up with this term alone. This thing here is going to be 1. And the f du, I'll call it f prime, and I'll call it g of u. Then we're going to go for the second partial derivative. Okay. The second partial derivative with respect to x, ddx, df dx. We have f of u is g. Okay. And see here, I call it. And then we have to take the total derivative with respect to u and the partial derivative of u with respect to x, which again is going to be 1. Okay, dg du, second order derivative of f with respect to u, that is g prime. Right, I can put another step here. F, 2 primes, g prime. And then we do the same for dy dt. Do the same for dy dt. Dy dt, you know, d of f dt, total derivative of f with respect to u, partial derivative of u with respect to t. But now this term is going to be different, because when you take the partial derivative of u with respect to t, you're not going to get 1, you're going to get v. Okay, you're not going to get 1, you're going to get v. And now we have to worry about the, okay, that's minus plus, right? Minus plus. Minus plus, we're doing for the most generic case. Minus plus f prime minus plus g of u. That's how I defined it. Then we go for the second derivative. The second derivative of y with respect to t, partial derivative. d dt, right? Y is f of u. Okay. F of u. D of f of u with respect to t. Okay, let's see what I'm doing here. Yeah, this we did that, right? Okay. Here you go. That's this one here. Right? dy dt, which is also df dt, is going to be equal to this guy here. I'm going to even put aside so you can consult it more easily. Okay. And I'm going to do another step, right? You go like that. And my v is a constant, consequently can be taken out of the parentheses. dg dt. we do the chain rule. Total derivative of g with respect to u, du dt. And we have the minus and plus here, and the minus and plus here. Minus and plus from this one, and minus and plus from this one here. Finally, we have this v square dg du. Okay, or 7 more minutes to go. There you go. Okay, dg du is d2f du2. All right, and it should be f here, right? f2 prime. V square f2 prime. And now we go back to this equation. Let's see if that solution that you saw satisfied the wave equation or not. Right? d2x dx2, d2y dx2. Let's see here. Okay, is this guy here. Let's put it here. Good. Okay. And I put it in terms of the total derivative, not the prime notation, right? d2y dt2, okay, is v square f2 prime. But don't forget, we still have this term here dividing here. And now look what we did. We prove that this side here is equal to this side. So we got it a reasonable relation, right? Basically what I'm saying here is that 0 is equal to 0 or 1 is equal to 1. Okay, we can, so this relation is true. If this relation is true, it means that f of x minus vt, f of x plus or minus vt is a solution to the wave equation. Okay, that's proof that this function, these two functions here satisfy the wave equation. Okay, so how are you doing there? So you should expect some types of problems like that in the, and then you can, you can even repeat that. Repeat that for cosine of kx minus vt, right? Repeat that and see if you get a solution for the wave equation. I did that here. You can also try something like that, see if this one satisfies. Now it looks like x minus vt, but it's not exactly like that. You have a square root separating those two terms. See if it satisfies or not. Okay, and so on. Okay. So I think we can stop now. I'm quite sure it's going to be, it was very intense, right? Lots of things to derive. I want you to practice at home. When you do that for the first time, it's very difficult, but then as you do more and more often, it becomes second nature to you all, okay? Any questions? Yeah.
Are we going to be expected to derive this, Professor?
Yes.
Okay,
yeah.
Just checking.
There will be some problems related. It's going to be simpler than that, okay? But yeah, you are expected to derive that, to know how to derive that.
Thank you.
And then you can practice with those other examples I'm not going to cover. I'm going to leave for you to take a look. And then you can invent your own relations. You can come up with another example like that, like the case of not this one, but this one here. X minus vt. Did I do that in the other one? Let's see. I don't think I did. I did for the cosine only. Yeah, I did for the cosine only. See if this one also satisfy the wave equation. Okay, and we can even do for both of them, plus and minus. Okay, that should be, you know, example 4. Okay. Good, so we can stop now. I have office hours right now. If you wanna hang around to ask any questions, just stay around, okay? I see you again tomorrow. Stop sharing.